You hopefully now understand how the different types of power in a transmission line that is connected to both the source and load, how those powers are related to each other. Again, we have the power delivered from the source, we have the power absorbed by the load, and then we have the net power flow along the transmission line, which we know, of course, to be the difference between the power associated with the incident wave and the power associated with the reflected wave. And we know that the delivered power and absorbed power are equal to each other by conservation of energy, and that is because the transmission line is a lossless transmission line. And of course that means that the net power flow at any point along the transmission line is precisely the same. The transmission line, because it's lossless, cannot alter that net power flow. So basically the rate at which energy comes into the transmission line must be equal to the rate of energy that comes out of the transmission line. The question we're left with, though, is how do we numerically determine these values, given some transmission line, specific transmission line characteristic impedance and electrical length, given a specific load and a specific source. How can we determine the rate at which energy is flowing along this transmission line? And that's what we hope to determine in this unit. I contend there's at least 4 different ways that we can determine the rate at which energy flows along this transmission line. And so the first way is, let's say that we know now the total voltage and the total current unambiguously. Once we've terminated our transmission line with a specific load and have connected a specific source, we can determine both the total voltage and total current, again, without any unknown constants, without any ambiguity. And of course, here are the solutions that we presented. I would not recommend trying to calculate these values, but instead, if I want to find the total voltage and total current, go ahead and apply boundary conditions or other strategies for trying to determine the V0 plus and the V0 minus, the unknown wave coefficients, and from that get the total voltage and total current. The point here is that we can determine unambiguously each of these two functions. Once we do that, we can evaluate these functions at one specific point, and that point is at the very end of the transmission line where the load is attached, at the index that we are defined as purple ZL, some number that we arbitrarily assign to the end of the transmission line where that load is attached. So we insert those numbers into these functions, and what we determine is a complex number, which is the voltage at the end of the line, and thus by KVL, the load voltage. Likewise, the current at the very end of the line, and thus by KCL, is the load current. Of course, once we know then the load voltage and load current, we can go through and determine the rate at which energy is being absorbed by this load. And of course, we use this expression. Simply take the complex voltage VL. It's complex because, again, we're assuming time harmonic voltages, sinusoidal oscillations with respect to some frequency omega, and then we multiply that complex voltage by the complex conjugate of the load current. And of course, the product of these two things provide us with a complex number, VL, and the conjugate of IL is a complex number. We then extract the real part of that number. We take that real part, divide by 1/2, or divide by 2 rather, and what we get is then the absorbed power, the rate at which energy is being absorbed by that load. So again, what we did was take the total voltage and total current on our transmission line, solve for that, and then evaluate it at the end of the line where the load is located, and take those two numbers, those two complex numbers, and from that we can determine the power absorbed by that load. The second way to determine the rate at which energy flows along the transmission line is to go back and try to determine the power associated with the incident wave along the transmission line and the power associated with the reflected wave, and then simply take the difference of the two, and that will be our net power flow. And there's a number of ways of doing this. Again, really what I'm just showing here is that we have, since we have the transmission line attached on either end, we have both boundary conditions, one for the load, one from the source. And so we can determine what this net power flow is. What is the incident power and what is is the reflected power. Again, I wouldn't really recommend solving for V0 plus in this way. I would go through and apply boundary conditions directly. I think you would find it easier. Oftentimes we have special cases in our circuits that can be applied to determine the value of V0 plus and V0 minus. So take advantage of those if they are available to you. But the bottom line here again is if we go through and we can analyze the circuit and determine the V0 plus and thus the power associated with the plus wave, the incident wave, and then V0 minus, and from that the power associated with the minus wave, the reflected wave, we simply take the difference, and that is the net power flow along the transmission line. The first way then we examined to determine the rate at which energy flows along the transmission line was to determine the power absorbed by the load. The second way then was determine the power, the net power along the transmission line by determining the incident power and the reflected power and then taking the difference. The third way then is we're going to try to directly determine the power delivered by the source, the rate at which energy is being delivered by the source at the beginning of the line. And the way we do this is really the same as we did for the power absorbed by the load. Once we know the total voltage as a function of position and the total current as a function of position along the transmission line, then we can go and evaluate the total voltage and total current at the beginning of the line where the source is located. And again, that index for the source is located we'll call ZG, purple ZG, some number. You simply evaluate total voltage and total current at that location at the beginning of the line, get those two complex numbers, and from that we can determine the power delivered by the source. So just as we did for the power absorbed by the load, we can use this relationship to determine the power now delivered by the source. This provides the rate of energy flow at a given location in the direction of which in which the current is defined as being positive. So we define the positive current as flowing from left to right, and therefore this number will provide us the rate at which energy flows from left to right. If we were to get a negative number, then we would conclude that the energy was flowing from right to left. But of course, in this case, we're going to get a positive value because the energy is being delivered by the source, is coming out of the source, and then is flowing down the transmission line where it is going down the drain, being absorbed ultimately by the load on the other end. So we know this value is going to be positive when we, again, define positive current as moving down the transmission line. So by KVL and KCL, we can see the voltage here at the beginning of the line is going to be defined by or equal to V sub S, and I didn't define on the circuit. I should have. V sub S would be the voltage here at the output of the source, and therefore the input to this transmission line. I sub S is the current at the output of the source, the current through ZG, and therefore the current into the transmission line there. And so again, we take the two values that we discovered from our telegrapher equation solutions, and from that we can calculate the power that is being delivered by the source, the rate at which energy is flowing out of the source. Oftentimes students will ask, well, which of these methods, three methods, should they use? Sometimes students are stressed about trying to identify which one because they want to make sure they get the right answer, and if they don't pick the right method of these three, then they'll get a value that is the wrong answer. But it's important to realize that, again, if we go back to our conservation of energy equation here, that the power absorbed by the load is equal to the power, the net power flow along the transmission line, which is equal to the power that's being delivered by the source. And so if we determine any one of these three, then the other two must be equal to them. In other words, all three methods will give us precisely the same method, or answer rather, the same numerical value, assuming of course that we've done our calculations properly. So we might argue that among these three methods, the one we should choose is the one that's easiest to us, the one that has the most information available to us, maybe again a special case that we can apply and use the one then where the answer is most easily determined. Now, having said all that, Generally speaking, we won't use any of these three methods. There turns out to be a fourth method for calculating the rate at which energy flows from the source down the transmission line to the load where it is absorbed. And that fourth method is what we'll look at next. The reason that we use this fourth method most often is because it is, generally speaking, the easiest of the methods in terms of trying to determine the rate of power flow. And this is a method that we've investigated earlier in this course. The idea of, if I want to know the rate at which energy is passing by a certain location in my circuit, what I want to do is determine then the equivalent circuit looking to the left, the equivalent source, and the equivalent circuit looking to the right, the equivalent load, and then go through and come up with a simple equivalent circuit that we can analyze to determine the voltage at that location, the current at the location, and of course from there determine the rate at which energy is flowing from left to right, the rate of power flow. And so this is how we might do that for a transmission line problem. Let's say we want to go through, and in fact this is typically how we'll say, let's try to calculate the rate at which energy is flowing out of the source. We're going to try to determine the delivered power of this source. And so we kind of draw a line right here at the beginning of our transmission line, and we say, all right, I want to go through and figure out what is the equivalent source looking to the left. Well, the equivalent source looking to the left, in this case, is simply the source. There isn't anything to simplify or transform. Some problems, there might be something, and we need to do a source transformation to come up with an equivalent source there. But generally, we write the plane at which we are determining the rate of energy flow. If everything is lossless, we write the plane right here by this source so that we don't have to try to do a source transformation. Instead, we look to the right, and everything to the right of this plane, where we're trying to attempting to find the rate at which energy passes by, everything to the right now is a passive structure, and we want to come up with the equivalent circuit for that passive structure. And of course, the equivalent circuit of a one-port passive device is its input impedance. And so we need to look at the length of transmission line and the load at the end, in this particular case, and try to come up with, well, what is the input impedance? Oftentimes we have special cases that we might be able to apply. There's a transmission line length of a half wavelength or a quarter wavelength. Maybe we have a load that's a special case. Maybe it is a matched load, and right away we know the input impedance is going to be numerically equal to Z0. Or some other special case that we can apply to directly determine the input impedance for a transmission line that is terminated in load ZL. If we don't have a special case, we can then use a Smith chart, and we can use the Smith chart to transform ZL to determine the value of Zn, rotating clockwise around the Smith chart until we get to that point. So the Smith chart comes in handy for these equivalent circuits. The bottom line is we replace everything that's looking to the right with its equivalent circuit now, and look what we have. We have about as fundamental and simple a circuit as we could imagine. The circuit that we've looked at several times earlier in the course, where we go through and we replace everything to the left of some plane with an equivalent source, and everything to the right of some plane with an equivalent load, the input impedance of that structure, and then to determine the voltage and current at that plane, it's a simple application of voltage division and Ohm's law. And once we have the voltage and current, then we simply take the voltage multiplied by the complex conjugate of the current, take the real part, divide by 2, and that is the rate at which energy passes across this plane from left to right. That procedure is therefore displayed here or described here. We go through with our simple circuit, and we can go through and use voltage division to find the value of Vn. And Vn, of course, is the voltage at the input of our transmission line. That is the value of the total voltage at the beginning of the line. And likewise, we can use Ohm's law here to determine In. And again, remember, In actually goes into the transmission line. So that is equal to the value of the total current at the load. And I should have just written this as Vn and In here at this point, because what we're trying to do with these two things is determine, again, the rate at which power flows across this plane. So to determine the rate at which energy is being delivered by that source, we simply take the voltage times the complex conjugate of the current, take the real part, divide by 2. Based on the previous analysis of the voltage and the current, or the complex conjugate of the current, we can write that expression in this form. Now, you could write this down, I suppose. I always discourage students from simply copying this equation and using the right equation there. Where we get to here is by a couple of simple steps. One is this fundamental relationship, which you do need to write down, in fact, memorize and make sure you understand. And then from that, we applied voltage division, which, again, a simple operation, a simple concept that certainly I hope you understand. Ohm's law, once again, something you can do. Complex conjugate, make sure you do that. And so you should be able to determine the answer very quickly once you determine quickly Vn and In without having to, again, copy down this equation and use it as some sort of template or recipe to get the right answer. Nonetheless, this is the algebraic expression of that answer. And the important thing to note here is we don't have any V0 pluses or V0 minuses. We don't have any gamma G's or gamma L's. The answer that we got is fairly compact. And really all the heavy lifting mathematically it really came into bear when we determined the input impedance. When we replaced that structure to the right of that plane with its equivalent circuit, with its input impedance. And so that is typically, again, the strategy we use for problems like this. We go through and we draw a plane right after the source. We take everything to the right of that plane, which is a passive structure, and we try to crush it down into a equivalent circuit, a simple lumped impedance, that is the input impedance. And once we do that, then again, finding the current and voltage and power is a very simple circuits problem that any freshman electrical engineer would be able to achieve. You might say to yourself, what if I'm not really interested in the power delivered by the source? I'm interested in the power that's absorbed by the load. Well, remember, by conservation of energy, the power absorbed by the load is the power that is being delivered by the source. Or you might say, well, gee, what I really want to figure out is what is the net power flow along the transmission line. Again, the net power flow is equal to the absorbed power and the delivered power. You might, and this is more frequently the case, you might be interested in, let's say, specifically the power associated with the incident wave on the load. And so still this technique would be useful. We can go through and determine the net power flow, which is the difference between the incident power and the reflected power. And if we know the relationship between the incident and reflected power, and we do for a terminated transmission line, simply the magnitude of gamma L squared, then is the relationship between those two values. We would have two equations and two unknowns. Again, the difference between the incident wave power and the reflected wave power is equal to the net power, which was just calculated from your reflection coefficient equation. That's your second equation. And then you can determine then both the incident wave and the reflected wave power for that case. So oftentimes, if you are looking for the power associated with one of the two waves or both, the first step you do need to find is what is the net power, the difference between the two. And you can determine that, again, with this result. Find the power delivered from the source using the equivalent circuit. And once you have that power, you can usually go and figure out then the remaining two values of incident power and reflected power. To emphasize again, all of these methods provide the exact same number. All of them are valid. Again, we choose the one that is easiest for us to calculate, generally speaking. And most of the time, that is the fourth method that we discussed here, where we replace a large portion of the circuit with an equivalent circuit, and then simply evaluate the simple equivalent circuit that results because of that. So again, I get over over the years, I've gotten many questions where students will say, gee, you told me this was the power delivered or power absorbed or the net power, and then you told me that this is the power delivered or the net power, and which one is it? Make up your mind. I mean, this looks nothing like this. Well, it turns out these are equivalent. They have the same values, will lead to the same value. They will give you the right answer. And what really happens here is this input impedance. A lot is hidden in that. A lot of our transmission line theory and such is hidden in that input impedance, because we had to go through and determine to what extent or how does the transmission line transform our load impedance into an input impedance. Again, we use special cases for that, or we use a Smith chart to calculate that value.